Now that we've had a discussion about improper integrals, we can talk about our first test about whether or not a series converges or diverges, and it's conveniently called the integral test. Now, in terms of a process about how do you know which test to use, ideally you'd like to be able to look at a series and use the nth term test for divergence. Is the nth term something other than 0? If it is something other than 0, then you know the series diverges. If you do get 0, you don't know anything. Perhaps it's a telescoping series, so you might use some of those tricks to evaluate it. Perhaps you can recognize it as a geometric series, so you can know based on the value of r whether it converges or diverges. But if you can't recognize those things quickly, now you need to choose from a bag of tricks on what you do. And one of the tests you might use quite a bit is the integral test. So for the integral test, if a function, f, is positive, continuous, and decreasing. So those are the initial conditions that must be used must be the case in order to use this test. For x being greater than or equal to 1, and we'll explain where that came from in a second, and a sub n is equivalent to the function f of n. So this is the expression that will give you any term in the series, right? The rule to generate the terms. So if those conditions are met, mainly that your series is positive, continuous, and decreasing, then our series from n equals 1 to infinity that's generated by this rule and the improper integral from 1 to infinity of f of x dx, right? So we're relating the rule to the function a sub n and f of n or f of x. Then they're related in that either both converge or both diverge, right? They're doing the same thing given those conditions. So for example, let's say we want to know something about the series that goes from n equals 1 to infinity of n over n squared plus 1. Now the nth term test, if we tried to use that first, the limit as n goes to infinity of n over n squared plus 1 is 0. It's 0 because the degree of the denominator is bigger than the degree of the numerator. So this limit's always 0. We can't conclude anything because the nth term is 0. So we have to do some more things. And what's going on with this series. Now, if you look at the terms, the first term would be 1/2, and the second term would be 2/5, and the third term would be 3/10. So our terms are going to be positive, and they are decreasing, and it is continuous, meaning every value of n I can use. So I can use the integral test to figure this out. The integral test tells me that that series is somehow related to this integral, the integral from 1 to infinity of x over x squared plus 1. And if this integral converges, then so does the series, and if this integral diverges, then so does the series. Now recall that in order to integrate this, we have to consider the limit, and I happen to use b, as b goes to infinity, of the integral from 1 to b of x over x squared plus 1 dx. Now when I look at this, what I'm thinking is use substitution as a technique, because the degree of the numerator and denominator differ by 1. If u equals x squared plus 1, then the derivative of u equals 2x dx, or 1 du equals 2x dx. And the way I do it, that means that 1/2 du divided by 2 equals x dx. I'm able to substitute for all of my parts. This means that the limit as b goes to infinity of, well, originally my limit of integration was 1, and now I'm changing everything into terms of u, so my lower limit will become 2. Why? Because when x is 1, 1 squared is 1, plus 1 is 2. When x is 1, u is 2. To b squared plus 1. My class recently called me out on this, that I wasn't changing my limits of integration. X squared plus 1 is equal to u. X dx is equal to 1/2 du. I'll write it this way for now. And now this I can integrate with respect to u. Now I know that the integral of 1 over u is the natural log of u. So this was going to become the limit as b goes to infinity of 1/2 the natural log of u. I haven't changed anything back, so this is going to go from 2 to b squared plus 1. Now I usually don't write that down because I always change it back, so let me change it back real fast. And the limit as b goes to infinity of 1/2 the natural log u was equal to x squared plus 1, and this really ought to be an absolute value. And this will be from 1 to b. Now when I substitute b in, I haven't taken the limit yet, so I still need to write this down. The limit as b goes to infinity of 1/2 times the natural log of b squared plus 1 minus 1/2 the natural log of 2. This part, when I plug infinity in, I get infinity squared plus 1. That's huge. And the question that goes with natural log is e to what power is this huge thing? Well, that's going to be infinity. The second part, e to what power is 2, is some number, but subtracting that number, or adding that number, whatever the case may be, from infinity is irrelevant. This is a divergent integral. And because the integral is divergent, so is the series. They must do the same. Now, they're not equal, but we can conclude the same thing about them. Let's try one more example with the integral test. So let's look at the integral, the sum of the series from n equals 1 to infinity of 1 over n squared plus 1. Now it is the case that this thing is always decreasing because the terms would be 1/2 plus 1/5 plus 1/10. And just a clarification on if the terms must always be decreasing. It could be the case that you could see your terms in your series at first increase a little bit, but then steadily drop. So this little blip at the beginning becomes irrelevant because in general it's decreasing, right? So it's not necessarily what happens in the first few terms, but what's the general trend over time. Sometimes you'll see that the first 2 or 3 terms increase and then it heads back down, and that still applies in terms of the integral test. Now, it does meet the conditions, so we're going to want to consider the integral from 1 to infinity of 1 over x squared plus 1 dx. And at this point you ought to be saying, hey, I know what that is, but even if you can't remember, you might need to look it up. We want to take the limit as b goes to infinity of the integral from 1 to b of 1 over x squared plus 1 dx. This is the identity for arctangent. So this is the limit as b goes to infinity of arctangent of x from 1 to b. By substitution, we have the limit as b goes to infinity of the arctangent of b minus the arctangent of 1. As b goes to infinity, what angle has a tangent value of infinity? As we saw earlier, that's pi halves because of the graph. What angle has a tangent value of 1? You should know that that is pi fourths, and their difference is pi fourths. Because the integral converges to pi fourths, the series also converges. It doesn't necessarily converge to pi fourths, we just know for a fact that it does converge. Right, so all this is a signal of convergence, nothing more than that.